Here we go. We are recording. So yesterday, we talked about differential equations and gave an introduction to differential equations. You know, it's an equation that involves some derivative or derivatives of a function. And we talked about what it means to be a solution of a differential equation. A solution is a function that satisfies the equation, right? So we looked at that. We talked about particular solutions versus general solutions, and we talked about solving initial value problems. So today, we are going to discuss how to actually find the general solution of a differential equation. The easiest types are the ones we talked about yesterday, where the easiest types are where you just have like the derivative of y equals some function of x. How do you solve that? You solve it by just integrating. Integrate y prime dx, you integrate f of x dx, and you get y equals some antiderivative. And you obtain the general solution with that plus c on the end, the general antiderivative. So this is the simplest type of differential equation, but those really simple ones aren't as common. One of the most common types of differential equations we see in applications like physics, engineering, chemistry, other places, is a type of differential equation called a separable equation. So let's look at the format of a separable equation. A separable equation is of the form some function of x times some other function of y. Or if it's not exactly in this form, it can be put in this form. So sometimes you may be presented with a differential equation that isn't exactly in this form, but it can be rearranged into something of this form. A function of x times a function of y. The reason it's called separable is because essentially the way we approach this is to separate everything about x on one side and everything about y on the other side. So what we're going to do is we're going to do a very strange thing. We're going to take this notation for the derivative of y with respect to x, and we're going to treat it as a ratio of differentials, which is more or less valid. Okay, there's some sort of iffiness about that, but more or less, we're not going to get into the weeds. More or less, this is a ratio of change in y over change in x for very small changes, right? So what we can do is we can multiply both sides by that change in x, and that will cancel out the dx. Then the other thing we can do is divide both sides by g of y, and that will cancel out the g of y on this side. And what we obtain is an equation that looks like this: 1 over g of y times dy equals f of x times dx. And now it's separated, right? All y's on the left, all x's on the right. What do we do next? Integrate both sides. So from here, we would integrate and solve for y. And this is a strategy for finding the solution. So this would actually allow you to obtain the general form of the functions that solve this differential equation. So let's look at an example, a nice simple example to start with. Oops. Okay, so for our first example, let's look at y prime equals ky for some constant k. Okay, this is a separable differential equation because f of x is essentially just 1, or maybe k, doesn't really matter. Yeah, let's say f of x is k. Let's say like our f of x is a constant, that's k, and our g of x is y, like that, just like that. So we can approach this in the strategy in the way that I described above, right? If this y prime, if we interpret it as a ratio of differentials, right? Then what we're going to do is we're going to divide both sides by y. We're going to multiply both sides by dx to cancel things out. So we're canceling y's on this side. We're canceling dx's on this side. Now we have 1 over y dy equals k dx, and we integrate both sides. Oops, thanks, g of y. Thank you. I wrote g of x. It's supposed to be g of y. Okay, let's see what we get. You integrate 1 over y, and we get the natural log of the absolute value of y, plus some constant, call it c1. You integrate k with respect to x, and you get kx, plus some other constant, call it c2. We can subtract constants over, canceling out this one, and we basically just have kx plus some other constant. It's going to be c2 minus c1, but those constants, both of them could have been anything, right? So when you integrate both sides of an equation, you really actually only need to put a plus constant on one side or the other, because whichever side you put it on, you could just gather all the constants on one side, and it's still an arbitrary constant over there. The difference of two arbitrary constants is still arbitrary. It could still be anything. Okay, so there we go. So we got that. And now we want to solve this for y. If I have the natural log of y equals kx plus c, I want to solve that for y. I can do y equals e to the power kx plus c. And technically I have a absolute value of y here. So this could be plus or minus. Okay, so y is the sort of positive or negative e to the kx plus c. Okay. Oh, sorry, the kx plus c, the plus c, I put the plus c in the wrong place, didn't I? The plus c is up here the plus c is in the exponent, right? Interesting. So with the plus c in the exponent, how can we interpret that? Well, when you add a constant to an exponent, you remember how you can sort of split that up into, here. Do you remember this property that like e to the a plus b is like e to the a times e to the b, like that? Yeah, I can break this apart. So I can have y equals plus or minus e to the power kx times e to the c. And this e to the c, this is still an arbitrary constant. It's actually an arbitrary positive constant because it's a power of e. But it could be any power of e to the power whatever you want, e to the power positive number, e to the power negative number. And, you know, the output of that e to the x function, the entire range of outputs is all positive numbers. The only thing that you can't have there is 0. The only c value that doesn't work is 0. But, the only value of e to the c that you don't get is 0. So what I'm actually going to do is replace the entire e to the c by another c, because e to the power constant is still a constant, and it's still mostly arbitrary. The fact that it's a power of e means it does have to be positive, but actually the plus or minus we got from the absolute value means that we can then sort of adjust this again to say that, in fact, that c could actually be that constant, that arbitrary constant, like factor in the front here, could actually be any constant factor, anything other than 0, positive or negative. So it's like we lost the negative numbers, but then we gained them back again because of the plus or minus from the absolute value. So yeah, so that's how we obtained that general solution to this differential equation that I told you about yesterday, right? I already told you this was the answer yesterday, but without any explanation. Now, here's proof, right? Here's the explanation. So there's a question in the chat. Why is it the natural log of the absolute value of y? Doesn't it need to be positive y to have a positive 1 over y? We don't have to have a positive 1 over y. We don't have to have a positive y. Y could be negative, I believe, because k can be any constant. So I think there's nothing in particular requiring that y be a positive number or anything like that. In order for us to apply the natural log, we have to we can only put a positive number into the natural log. So that's why we take the natural log of the absolute value of y. If y was negative, now we do an absolute value to make sure it's positive, to make sure it's a valid input to the log function. And that log of a negative y is still an antiderivative for 1 over y. It's the antiderivative you would want on the left side. So this is something, the fact that this is the antiderivative of 1 over y, that we talked about that back in Calc1, why there's an absolute value there. Yeah. Yeah, okay, so let's do more examples. Okay. Any questions before we do another example? Let's do it. Okay, so for this next one, we're going to do y prime equals a function of x, like x squared, times a function of y. Let's do a linear function of y. Take 2x plus 5. Okay, so this is dy over dx, right? So what we're going to do is we're going to rearrange things. We're going to divide by this and put the dx over there. So we're going to get like 1 over 2y plus 5 dy equals x squared dx. I'll write the dy over dx here so it makes it clear. That guy is going that way. This guy is coming this way down here. So now the 1 over the 2y plus 5 is in the denominator over there, and the dx is in the numerator over here. Okay. Now we integrate. Let's see what happens. How do we integrate the left side there? We can do a little u sub here. U equals 2y plus 5. So du is 2 dy. And so 1/2 du is dy. So what I can do to make this a du integral is that. Okay. And on the right side, I'll go ahead and integrate that because that's a little easier to do. 1/3 x cubed plus c. So we have that. So there's a little u substitution on the left. So now when I integrate, I get the natural log of the absolute value of u. And that's I'll multiply both sides by 2. I'll times by 2 times 2. To cancel out my 1/2 over here. So I got the natural log of the absolute value of u. Now u was 2y plus 5, right? Now I'm going to distribute multiplication by this 2 here. 2 times 1/3, 2/3. But here, if I take my arbitrary constant c and I double it, it's still an arbitrary constant. So I'm not really going to change that. I'm not going to bother writing 2c. This is something that we end up dealing with a lot here. We end up like looking at arbitrary constants and doing operations to them, but then checking to see if it's still arbitrary, right? Could c still be any number? It sure could. If you double it, it's still any number, right? Then we do this maneuver like we did last time here. We do the e to the power thing, right? So we take our base e down here from the logarithm, raise it to that power, and set that equal to whatever's on the inside. We got our absolute value of 2y plus 5 equals e to the power of 2/3 x cubed plus c. And we can break that out into the e to the c again, right? Which is pretty much an arbitrary constant except for the positive negative, but that, like last time, is going to be dealt with by our absolute value. So we still have arbitrary constant times e to the 2/3 x cubed, like that. And now we have to just solve for our y. So we got to subtract 5. Now we have 2y equals that stuff. C e to the 2/3 x cubed minus 5. And lastly, we'll divide both sides by 2. So y equals that. I'll just write it one more time. Minus 5 all over 2. And that is the general form of the solution to this differential equation. Let's discuss how we can check our work. Let's use Desmos. Okay, how do we check our work? We type in our answer as a function. So let's give it the name f of x equals a fraction. In the numerator, we have c times e to the power, and then in parentheses up here, I'm going to put 2/3 x cubed, right? And then coming out outside of that exponent, we have then a minus 5, and it's all over 2. Now, I put this arbitrary constant c in there. I'll just make a slider for c. And so now I can look at what these solutions look like. Here are my solutions, right? Here's the solutions for various constant values, positive and negative constant values. Okay, so these are what the solutions look like. And now if I want to check to make sure they satisfy the original differential equation, looking back at our work here, this was the original differential equation, right? It's y prime equals x squared times 2y plus 5. So what I want to do is I want to graph y prime. That's my f prime of x. There we go. So that green graph is now the derivative. That's y prime. And then I can graph x squared times, in parentheses, 2y plus 5. Except I don't want to write 2y plus 5. In place of my y, I want to put f of x. And so now I can see that the two graphs, the green and the purple, are indeed equal to each other for all values of this constant. Now, this confirms that what I found here, that these are indeed all solutions to the differential equation. Oops, sorry. What it doesn't quite confirm is that these are all of the solutions, that there's no other solution. So that is harder to prove, or harder to check. But the work that we have done was exhaustive. There was no, this basically is there is no other way that we could have gotten a solution, right? We found the general antiderivative here when we were differentiating. We were finding general antiderivatives, and that represents all of the possible antiderivatives. So it's this process captures the full solution, okay? The full range of possibilities. All right, so that's how you can use Desmos to check your answer. So let's do another one. This one's a little trickier. All right, this is not just f of x times g of y. Right? It's jumbled up. We've got a term with an x times y. We've got a term with a y, a term with an x, and a constant term. Well, what we can do is try to factor it. Let's do factor by grouping. This is something you might not have done since like basic algebra class or intermediate algebra, maybe. Let's factor by grouping. So from the first two terms, we could take out a y, right? So we can do like y times 2x plus 3. And then from the second two terms, we can take out a -2. We can pull out a -2 from those terms. So like -2 times 2x plus 3. Oh, hey. And it's kind of coincidental, but we do actually have the same factor showing up. So we can factor that out. And now we have 2x plus 3 times y minus 2. And hey, there we are. Now here we have our f of x times g of y format that we were expecting. So then you can go about solving the way we did the previous one. So I actually don't think I'm going to bother finishing that one. I'll let you guys finish it. I just wanted to bring up this example as to show you how sometimes there's a little work that goes into figuring out how it is f of x times g of y, right? You might have to rearrange things. Factoring is one example. You might just be moving things from one side of the equation to the other. But yeah, it might be a little bit of algebra to rearrange it until it is in the format you want it to be in to do the separation of variables. Okay. All right, guys, your turn. I want you to try y prime equals x over y. Try solving that one. I'm going to give you a few minutes to work on that, okay? Sound good? Give me a thumbs up. You guys want to do a Jamboard? Jamboard is your space. If you want to do it, go ahead and if you guys want to use a Jamboard, go ahead, head over there and feel free to use it. Just clear away anything that was there. It's your space. I don't use that board for any other class. It's unique to this class. So yeah, I'm just going to pause the recording and give you guys about 5 minutes to work on this, either alone or together as you see fit. My pause button. Resume recording. All right, we're sorry. I forgot to, for those watching this later, I forgot to start the recording again. We just started going over this problem. So here's the steps. We got to this point. We're solving for y. We have the square root of x squared plus c. And I just asked, is it the same as just doing that? Is it the same as just having the plus c on the outside? So the common answer we're seeing here is, I'm getting the answer y equals x plus c. Let's get over to Desmos and explore this question. I can agree with you that if it is okay, if it's okay to just put the plus c on the outside of the square root, then y equals x plus c should indeed be a solution. So let's check it. Here's x plus c. So as expected, we just have straight lines with slope of 1, and changing c simply moves the line up and down. It's right, changing the y-intercept, right? So now let's check. We want to see if y prime equals x over y. So y prime is a constant. Y prime is 1, right? So graphing that, y equals y prime, that's a horizontal line there at 1. And then if I do x over y, it's x divided by f of x. Oh, yikes. Those aren't the same at all, are they? Those are not the same. All right. If we scratch that, this must be wrong. This must be wrong because it didn't work. So these are indeed not the same. You guys made the common mistake of distributing a square root over addition. This is not correct. You can't do that. Same reason you can't distribute powers over addition, right? It doesn't work that way. So what we want here instead is we want that square root of x squared plus c, with the plus c on the inside. And as you can see, now this is a very different graph than the one we had before. This is not that straight line. This is a curve, right? It's kind of an interesting curvy shape. I'm not quite sure what that is. It's not, it might be a hyperbola. It might be like half of a hyperbola. Anyway, now we can see that its derivative is this nice black line right here. And the x over f of x does yield the same result. So that square root of x squared plus c, that is a solution. That is a solution. And that's for, I had absolute value of y. So actually, I guess there's two solutions here. There's y equals the positive square root of x squared plus c. And there's y equals the negative square root of x squared plus c. Which we can check that one as well. Let's just throw a negative sign in front of our f here. Ah, yes, there we go. And yet again, we have the f prime and the x over f in agreement, which demonstrates that these are equal, right? F prime and x over f are agreeing with each other. So there is our solution to that one. Okay, so there's a cautionary tale, right? Careful with exponents, careful with square roots. Make sure to keep your c, carefully keep track of where c is, because it makes a big difference whether you put it outside or inside, whether it's multiplied or added. Like, these things matter, okay? And you can end up with an entirely wrong solution to a differential equation if you don't pay careful attention to where that arbitrary constant is, okay? It's fun to mess around with these things and look at the different possible solutions. These are what all the solutions look like. Look at these ones. Yeah, and these different. Yeah, I like it. I think they are hyperbolas, I do believe, because we got the negatives down here as well. I think that's a hyperbola. And if you, oops, if you look at those two red graphs, I think those make the two legs of a hyperbola. I hope I'm not wrong. I could be wrong. Maybe it's not a hyperbola. Maybe it's some other similar curve. All right. So it's 12:37. That pretty much wraps up that topic. But we should do a little more today. Now that we've learned about how to solve differential equations, there are some applications we can learn about. Okay. We do two applications. So in the first application, we're going to be talking about concentration in brine with inflow and outflow. This is the sort of thing that you encounter in like complex industrial applications where you're doing some sort of mixing of chemicals in a big tank or whatever. You've got some sort of inflow of solutions and then some sort of outflow after mixing. And you got to pay careful attention. You got to carefully control the concentration of things. This is, by the way, well, here, let's let me lay out the problem, and I'll tell you what this reminds me of. So this is a tank. It's got some fluid in it. right? We have salt brine, which is basically just a salt and water solution. This is going to be a 100-liter tank. And we've got inflow and outflow. So flowing in, pumping into the tank, we have a 0.5 kilogram per kilogram of salt per liter solution. That is what's flowing into the tank, and it is doing so at 2 liters per minute. So we have a concentration of brine flowing into the tank, a brine with a certain salt concentration flowing into the tank at a certain rate. And then we also have a brine flowing out at 2 liters per minute. Now, what is the concentration of the brine that's flowing out? Well, it depends, because inside here, we're going to assume that we have mixing. Mixing occurs inside the tank. So we're just going to assume that the brine inside the tank is mixed sufficiently so that it is homogeneous, like same concentration throughout. And then we have an initial starting concentration. Initial concentration of 4 kilograms of salt in the entire 100 liters. So that would be 4 divided by 100 is 0.04 kilograms per liter of salt. That makes sense? So the quantity of salt in the beginning is 4 kilograms, and that's in the entire 100. That makes sense? So it's critical to note that here that the volume of brine in the tank is not changing because the inflow rate and the outflow rate are equal to each other. Okay, but there is going to be some change over time in the concentration. Just looking at it, intuitively, we can see that if we start with a concentration of 0.04 kilograms of salt per liter, but we're putting in 0.5 kilograms of salt per liter, sorry, if that's what we're putting in, right? Then that concentration, salt concentration of the brine that's going into the tank is a lot higher than that which is in there to begin with. So over time, with that mixing and the inflow outflow, over time with the mixing, we're going to have that salt concentration is going to increase, right? So how are we going to approach this? We're going to approach this by setting up a differential equation with a function. So first we have to define what function are we going to be paying attention to for our differential equation, okay? So let's have f of x, or let's call it y. Y equals the kilograms of salt in the tank. Okay, if we set y equal to the kilograms of salt in the tank, then we can look at rates of change in that. All right, and that'll help us set up our differential equation. Okay, hang on a second. So to calculate what we want to do is think about like the rate of salt entering the tank and the rate of salt exiting the tank. We're going to pay attention to the rate of change in the quantity of salt over time. And this is going to be basically an inflow rate minus an outflow rate. Okay, so it's going to be a differential equation equal to the difference, the subtraction of two things. Now, what are those rates? Well, let's look at them one at a time. The inflow rate is we want it to be in basically kilograms per minute. Okay, so what we have is a brine with a concentration 0.5 kilograms per liter, and it is flowing in at a rate of 2 liters per minute. So we can multiply those together, the concentration times the rate at which the volume is going in. And we see when we multiply about those, we get the liters canceling out, and we get a half times 2, which is 1 kilogram per minute. Okay, so this information together gives us a like inflow of salt of 1 kilogram of salt per minute, right? It's 2 liters per minute, but multiplied by a half a kilogram per liter. So we're just paying attention to the quantity of salt in kilograms. So that's our inflow rate. What about the outflow rate? Well, the outflow is going to be based on like the amount of salt which is in the tank already. And it's a 100-liter tank, right? So here's how we can think about it. We're going to say the concentration of the salt. So we're going to calculate it the same way we did the previous one, where we're going to calculate it with concentration concentration times the volume rate, right? But the concentration is a little different, because the concentration is just going to be like however much kilograms of salt is in the tank right now, which is our y variable itself. That's how many kilograms divided by the total volume of the tank, which is 100 liters, right? Yeah. Is this lesson being recorded? I believe so. Yeah, we're still recording. So y kilograms divided by 100 liters, that's the concentration of this brine after mixing it together. And then it's also leaving at 2 liters per minute. So we multiply by the same thing, and we get our liters canceling, and this reduces to y over 50 kilograms per minute. So what that means is that the outflow rate of salt depends on the concentration of salt, depends on the amount of salt which is currently in the tank. So we end up with this differential equation of 1 minus y over 50 being equal to dy over dt, right? It's this differential equation. The rate of change does depend in part on the current value of the function. Okay. So now this hopefully is something we can solve. Let's figure out how we can solve this. Okay, so this is the setup. All right, this is all like the application component. Now we can figure out how to actually solve this equation. So we can just turn our attention to the mathematics alone and ignore what it means for a little while. But before we do that, why is it y? Do you mean, Braden, are you asking about why is it y right here? Or yes, here. Yeah, okay, it's because to figure out how much salt is leaving the tank every minute, it depends on the current concentration of salt in the brine. And that would just be the kilograms of salt that are in there divided by 100 liters, because the volume is staying constant at 100 liters. Now, how much salt is currently in there? It's y. That's what our variable represents in the first place, right? Sorry, that's my mouse doing that. I apologize. So that's why there's a y in that concentration. Does that make sense? Okay. So we're low on time. Maybe what we should do is hold off on this a little bit, You guys want to just cut it here, and then maybe you can try to solve this on your own. And we'll go over it tomorrow. Not tomorrow. We'll go over it on Monday. I think that sounds good, right? So yeah, see if you can solve that. It is separable. I'll tell you that it is separable. It's a little tricky to separate, but you can do it. Just a little algebra. And then when we solve that, it'll give us a solution for a function that describes the amount of salt in the tank at any given time, which is pretty sweet. All right, folks. See you next week.